Hello, I'm Robert Metzger. I am the project manager responsible for Convex's new product, the Application Compiler. I would like to introduce two guests I have with me today to help explain how to use the Application Compiler. This is Jean Suplick. She works in the Convex Technical Assistance Center answering questions from customers about using the Application Compiler. Next to Jean is John Coles. John works in the Convex Sales Support Organization. He is an experienced user of the Application Compiler and has ported a number of applications to Convex systems. This video is intended to teach experienced Fortran and C programmers how to use the Convex Application Compiler. The presentation has two parts. In part one, we will introduce the basic concepts of the Application Compiler. In part two, Jean and John will help me to walk through the process of using the Application Compiler. We will answer questions the users have most frequently asked about the Application Compiler. In part one, we will cover the following topics: background, inter-procedural error checking, inter-procedural constant propagation, automatic inlining, inter-procedural pointer tracking, and the user interface. Let's begin with some background on why the Application Compiler was developed and how it might help you to use your Convex system more productively. In the mid-1950s, the first Fortran compiler was developed. The developers knew that their compiler must generate code nearly as good as that which was written by assembly language programmers if the concept of a high-level language was to be accepted. They designed Fortran so that they could generate efficient code for the constructs it contained. By 1966, Fortran had gone through several revisions and had become an ANSI standard. In the 1970s, optimizing Fortran compilers became available. Fortran was used for scientific programming, and high performance for compute-intensive applications was essential. The introduction of the Cray-1 vector supercomputer in 1978 motivated many new developments in compiler technology. The early 1980s saw the introduction of compilers which performed vectorization by matching simple patterns. In the second half of the decade, companies like Convex introduced compilers which performed automatic vectorization and parallelization. Now, in the 1990s, the technology which will continue to improve the performance of scientific applications is inter-procedural analysis. Optimizing compilers have become progressively more sophisticated, and the scope over which they perform optimizations has steadily increased. Today, there are still many compilers which only perform optimization on code blocks, sequences of statements ending in a control flow construct. Some more advanced compilers perform optimization on an entire procedure. Until now, no commercially available compiler has performed full optimization across procedure boundaries in a general manner. The fundamental problem for compilers is visibility. Programmers know the behavior of the whole application, at least theoretically. Compilers need that same knowledge so they can fully optimize a program. The key to improving the effectiveness of optimizing compilers is enhanced visibility. Optimizers must answer two key questions in order to produce more efficient code. Which procedures and variables does each procedure refer to? What are the side effects of executing each procedure? Conventional compilers for some of the most commonly used languages operate on limited information. Fortran and common usage C compilers assume all procedure calls are correct. Languages like ANSI C and Ada require the programmer to provide extra information to check such calls. Even so, compilers must make worst-case assumptions about the side effects of a procedure call. Inter-procedural compilers, such as Convex's Application Compiler, have knowledge about all the procedures in an application. This makes it possible to find incorrect procedure calls and to develop precise data on side effects. Convex has a history of being first to bring unique software products to the marketplace. When Convex Fortran was introduced, it provided a level of automatic vectorization far superior to that of competing products. Convex was the first to introduce a C compiler that could perform automatic vectorization, and later the first to perform automatic parallelization as well. Convex was the first to introduce an Ada compiler that could perform automatic vectorization and subsequently automatic parallelization of loops as well. In 1990, Convex announced the Application Compiler, the world's first commercially available inter-procedural compiler. The Convex Application Compiler is the first practical application of inter-procedural analysis research in an integrated, language-independent compiler product. It develops the whole program view of an application and thus is more effective at finding errors and enhancing performance. How exactly does inter-procedural analysis work? It answers the questions of naming and side effects by performing a series of analyses. It first answers the naming question by performing call analysis, alias analysis, and pointer tracking. Call analysis answers the question, which procedures are invoked by a call? This might seem simple, but each language has features which introduce complications. In Fortran, the name of a procedure may be passed to a dummy argument which is declared external and referenced as a function or subroutine. In C, the addresses of functions can be taken, stored in variables, and passed as arguments. When these pointers are dereferenced, the function is executed. Alias analysis answers the question, which argument names refer to the same location? Aliasing occurs primarily as a result of passing arguments by reference, as is done in Fortran. Pointer tracking answers the question, which pointers point to which symbolic locations? Pointer tracking is performed for the benefit of C codes. Having determined which names refer to which procedures and memory locations, inter-procedural analysis then answers the side effect question by performing scalar analysis and array analysis. Scalar analysis answers the question, which procedures and subordinates use and assign which scalars. Array analysis answers the question, which procedures and subordinates use and assign which sections of which arrays. The difference between scalar analysis and array analysis is that with arrays, it is necessary to determine the geometry of the reference patterns. Scalar analysis simply determines whether or not a variable is used or assigned. The result of these analyses has determined the names referred to by procedures and the side effects of executing those procedures. Now, the application compiler can perform some inter-procedural optimizations. These optimizations include constant propagation, procedure cloning, and automatic inlining. Constant propagation answers the question, which global variables and arguments always have the same value on entry to a procedure? This information enables the compiler to tailor the called procedure to the context in which it is used. Inline analysis answers the question, which procedures should be substituted textually or inlined in place of procedure calls? Inlining not only tailors the called procedure to the context in which it is used, but eliminates the cost of the procedure call. When we began the application compiler project, we determined that there were several requirements for a successful product. It is important to understand these requirements in order to understand what problems the application compiler can help with and which problems it does not address. The primary requirement was to increase automatic optimization. Convex has been successful because we have enabled our customers to increase the performance of their applications. We have found that most of our customers don't have the time or inclination to change their code to maximize performance. They want to tell the compiler to perform automatic optimization and to see significant performance improvements. The second requirement was that the product provide language-independent optimization. This contrasted sharply with the university research on inter-procedural analysis, which has been focused on Fortran. More than half of our customers have licensed our vector parallel C product. We wanted to address the needs of all of our customers. The third requirement was that the product benefit scalar, vector, and parallel applications. This also contrasted with the university research, which has largely been focused on parallelism. We knew that most of our customers had single processor vector machines, either C1s or C2s. The next requirement was that the product must coexist with other software tools already in common use. Once again, this was a different approach than the university research into inter-procedural optimization. In these efforts, users worked in an integrated environment and had to learn new editors, debuggers, profilers, etc. The text editor programmers use is often a highly emotional issue, and we did not want to put barriers in the way of our product. We also knew that the product must have a reasonable compilation rate. The university research was oriented towards small programs. We needed algorithms whose cost increased linearly with the amount of code compiled. Another requirement was that the product must be independent of I/O devices. Most of the university research into inter-procedural systems required the user to work at a bitmapped graphics workstation. We knew that many of our customers still use VT100 or equivalent display terminals. Last, and definitely not least, we wanted the product to be easy to learn and to use. The application compiler is structured differently than traditional compilers. Understanding how the product works makes it easier to understand why the user interface is unlike a conventional compiler. Until now, the Convex compilation system consisted of separate preprocessors such as CPP and C++, distinct front ends for each of the three languages, and a common optimizer and code generator. The first step in developing the application was to reorganize the components of the existing compilers. Instead of two separate executables for C and Fortran, there now were three. The optimizer was split in half. With the scalar optimizer, there are significant limitations of other methods for automatic detection of programming errors. Lint doesn't do inter-procedural name or side effect analysis. Procedure compilers process only one procedure at a time. The application compiler provides a nice complement to these tools. The C-Lint program provided with Unix and the Fortran Lint tools available from third-party software vendors are definitely helpful. They detect mismatched numbers of arguments, mismatched types of arguments, mismatched types of call and return values, passing scalars to arrays, assigning constants passed by reference. There are errors, however, that these tools can't find unless they perform inter-procedural analysis. The application compiler uses the results of inter-procedural analysis to detect formal arguments which are alias to other arguments or common variables and which are assigned, which is a violation of the ANSI standard, global variables which are never assigned or initialized, and invalid array subscripts. We see here an example of inter-procedural error checking. The array subscripts are invalid, but there's no way to check them if the compiler only looks at one procedure at a time. When it examines the definition of the array and all the uses of that array together, it can determine at compile time that the program is erroneous. The application compiler uses the results of inter-procedural analysis to detect subtle programming errors that are difficult to find by other means. The next feature of the application compiler we will look at is inter-procedural constant propagation. The purpose of inter-procedural constant propagation is to find interface variables which always have the same value on entry to a given procedure, and having found them, substitute the constant value for the name of the variable. Constant propagation finds constants from a variety of sources, such as literals which are passed as arguments, variables which are passed as arguments, global variables which have been assigned before the procedure is executed, and global variables which have been statically initialized. We see here an example of one of the benefits of constant propagation. The loop in the subroutine cannot be vectorized by the Convex Fortran compiler. It doesn't know the value or the sign of the variable m, and so it can't tell whether or not there is a recurrence. The loop is vectorized by the application compiler. It propagates the 200 into the variable m, and then it is clear that there's no recurrence. The purpose of procedure cloning is to increase opportunities for constant propagation. Procedure cloning has three phases. First, the procedure is copied and renamed. Next, the caller is changed to invoke the new procedure. Finally, the new procedure is tailored to fit the context of its use. The application compiler clones procedures when constants can be propagated and optimization may be improved. Here we see an example of the benefits of procedure cloning. The loop in the subroutine cannot be vectorized by the Convex Fortran compiler. It doesn't know the value or the sign of the loop limit n and the variable k, so it can't tell whether or not there is a recurrence. The loop is vectorized by the application compiler. It makes a clone of the subroutine, propagates the -1 into k in the original and 1 into k in the clone. There is a definite recurrence in the original, but not in the clone, so the loop is vectorized in the clone. Automatic inline substitution is another optimization performed by the application compiler. Procedure inlining is the process of replacing the invocation of a procedure with the actual body of the procedure. This is quite different from procedure cloning. Automatic inlining is the process of finding procedures and procedure calls which, if inline, make the greatest improvement in application performance. The procedures and calls chosen for inlining are selected according to how frequently the call is executed and how large the called procedure is. Those procedures which are the smallest and which are the most frequently executed yield the most benefit from inlining. The aggressiveness of the inlining algorithm can be turned up or down based upon the needs of the user. Automatic inline substitution and inter-procedural constant propagation plus procedure cloning both address the same optimizations in a complementary manner. They both assist dead code elimination, dependency analysis, loop interchange, conditional vectorization, and vector strip mining. In order to understand the benefits of these two approaches, it's useful to compare and contrast them. Inlining and constant propagation follow different strategies for tailoring procedures to their calls. Inlining uses all the arguments at one call site. Constant propagation uses only the constant arguments at all call sites. Inlining increases performance by removing procedure call overhead. It doesn't always improve performance, however, because array argument reshaping may require extra instructions for address arithmetic, and because pathological coding styles may cause the compiler's register allocator to work suboptimally. Constant propagation never removes call overhead, but it is also less likely to cause a negative effect on performance. Inlining causes executable programs to become bigger. Cloning can also cause executables to become bigger, but not as much as inlining, since the compiler will reuse cloned procedures when the same constants are propagated at different call sites. Inlining and constant propagation use different selection criteria. Inlining chooses procedures based upon code size and call sites based on execution frequency. Constant propagation and cloning choose procedures based upon call sites which have arguments with constant values and procedures which have arguments used to control loops or compute array subscripts. A unique feature of the application compiler is its ability to perform inter-procedural pointer tracking in order to improve the vectorization and parallelization of C codes. Conventional C compilers must assume that global and formal pointers point anywhere in memory, or with ANSI C, at any object of the appropriate type. This means that any pair of pointer dereferences where one of the dereferences is a use and the other an assignment is a potential recurrence. Potential recurrences prevent vectorization and parallelization. The result has been that vectorizing C compilers aren't nearly as effective as vectorizing Fortran compilers if the user doesn't insert directives into his source or use command line options. The application compiler contains inter-procedural pointer tracking in order to overcome this problem. Pointer tracking symbolically analyzes the memory locations to which each pointer refers. If two pointers never point at the same location, there's no potential recurrence. The pointer tracking algorithm in the application compiler can handle static, automatic, and heap storage. The current implementation is limited to tracking pointers which have a single level of dereference. In practice, these turn out to be a large percentage of the total. Here we see an example of the benefits of pointer tracking. The loop in the subroutine cannot be vectorized by the Convex C compiler. It doesn't know the locations pointed at by P, Q, and R, and so it can't tell whether or not there is a recurrence. The loop is vectorized by the application compiler. It knows that these pointers never point at the same storage location, so it knows there's no recurrence. Now let's learn about the user interface of the application compiler. The interface to the application compiler is the build file and the build executable. Build automatically calls the appropriate compiler modules. Here you see one of the most common build files, and also one of the simplest. The source files are all contained in the same directory as the build file, which is denoted by the Unix shorthand dot. The programmer wants to compile all of these files for vectorization, and when they are compiled, they should be linked with the Fortran runtime library. Here is a slightly more complicated build file. The path to the directory containing the source files has been spelled out. While most of the files will be compiled for vectorization, the file main.f will be compiled at -01 optimization. In addition, the convex veclib library will be linked in. Now we have an example of a C application. It has been coded using common usage C syntax and semantics, rather than ANSI C, so we must tell this to both the compiler front end and the linker. In addition, the programmer has inserted a build command line option into the build file so he can see the results of pointer tracking. One final example shows a few more features of the build file. Here we assign a compiler option we wish to apply to all Fortran sources to the flags macro. Rather than referring to source files by directories, we have listed them out. We have also included an object file for which we have no source. Presumably, it has been annotated appropriately. The syntax of build files is relatively simple, as you have seen. You can specify the source file names directly or by the name of the directory containing them. You must specify which runtime library to link in, and may include extra libraries or link options if needed. You can embed any of the build program command line options directly in the build file so that you can have a record of how your executable was created. There are also a number of build file commands available to control the optimization process, which we will discuss in the second part of this presentation. Convex ships all of the important system libraries modified to contain inter-procedural information so that optimization occurs when they are linked in. The application compiler does not always improve the performance of a code, but when it does, the typical improvement is in the 10 to 25% range. These examples include codes which had already been hand optimized by a benchmark analyst, others which no source changes could be made on, both in C and in Fortran. Occasionally we see exceptional results. On the left we see a C code which had more than 100 million subroutine calls and whose performance more than doubled. On the right is a Fortran code which ran 430% faster when compiled with the application compiler. In this case, there was a lot of constant propagation, particularly to loop bounds, which made it possible for the compiler to perform loop interchange and to vectorize many loops. Convex is continuing to enhance the application compiler. We have a number of important enhancements planned for the future. The early adopters of the application compiler showed us that a number of enhancements are required in the library area. We plan to provide fully automatic library annotation in a future release, as well as other library support options. We believe that we can improve the effectiveness of inter-procedural algorithms by using profile data. We plan to provide a means by which users can designate profiler output to be used by the application compiler. The clear direction of supercomputing is to use more and more parallel processors. As more processors become available, we need to find new ways to use them. One important way to do this is to automatically parallelize loops containing calls. We are excited about the potential of the application compiler to help our customers make more effective use of their Convex systems. This concludes part 1 of this video. In part 2, we will address specific questions about how to use the application compiler.